So let's take a look at what we were given. Just to kind of start off the bat here, what is our generic formula for growth or decay? We're going to assume from here on out that our radioactive growth or decay is going to follow a continuous model. So for continuous growth or decay, what is our function here? What does this look like? Yeah, it's like the PERT formula, except instead of the P, what did we replace it with? A sub 0, just to indicate like, hey, we can talk about things other than money. All right, but really this is the PERT equation. And the thing that I really wanted to highlight here, the thing that piece that was missing, is yesterday we spent a lot of time kind of unpackaging this value of R here. That was really what we spent kind of the most time on. What is this value of R? But we didn't do that before when we were using this equation. In particular, what was this R here back before when we were doing our exponential growth and decay? Yeah, this is like the growth or decay rate. All right. And so I think a really cool observation that a lot of people made here was that this value of R, which we saw yesterday as this really complicated thing with a lot of like logs and all these kind of moving pieces. In this case, what is our value of R? That's that 6.7% decay, which as an R value is going to look like what? Negative 0.067. So we didn't look at too many examples of continuous decay when we were doing this kind of continuous function, but do remember that that R value will be positive for growth and negative for decay. That's kind of why I only looked at 1 plus R to the X, because R can either be positive or negative. So rather than kind of looking at 1 plus for growth, 1 minus for decay, it's kind of easier to just let R be positive or negative because that translates really, really well to what we do with continuous. All right. And so from here, we have a couple of different approaches, one of which is to say that my function is now A of t equal to A sub 0, in this case, our initial amount, 1356. That was a comma, not a decimal point. But if you did decimal point, you'll get something similar regardless. Times, actually, you'll get something exactly the same, times e to the negative 0.067 times t. And in particular, we are looking for the t value when what is true? What is the t value that we are looking for here? Yeah, that for when we have the half-life, which means how much of our original stuff is going to be left? Half of it. What is half of 1356? Did anyone do this? 678. So when 678 is equal to 1356 e to the negative 0.067 t. Solving this for t, what do I need to do in order to kind of solve this? Before I can start isolating the t, I first need to do what? Divide, get the e to the power by itself. I get that 1/2 is equal to e to the negative 0.067 times t. And what could I do from here to solve for t? We have a couple of different ways to kind of move forward from here. Yeah, I like writing it out as a logarithm. You could change the 1/2 base to e to the ln of 1/2 as well, and that would work. But I would probably just rewrite this as a logarithm. Either way, you should get that the ln of 1/2 is equal to negative 0.067 times t. And so solving for t, I get that t is equal to the ln of 1/2 divided by negative 0.067 months. Okay, which is a little bit silly to look at, right? We look at this doesn't do a very good job of actually telling us the amount of time. It's correct, it's accurate, but it doesn't really communicate the information very well. Rounding in my calculator, I get that this is about 10.35 months. So that was one way, perfectly valid. This is great. This looks good. I think not many people did it this way though, which is fine, because the observation that a lot of people made was, yes, my R value is equal to, in this case, R is equal to negative 0.067, but we also derived a formula for R when we are looking at half-life specifically. What else is R? R is also equal to ln of 1/2 divided by this t hat value, where t hat is just our half-life. And so we could also solve this equation for t hat, and that would work as well. I get that negative 0.067 times this t hat is equal to the ln of 1/2, and that t hat is equal to the ln of 1/2 divided by negative 0.067, which is exactly what we got before. Okay, so this works. Both of these work great. Either way is fine. And I saw today as well, or in this period in particular as well.
Please pardon this interruption. This is a drill. AED team, please report the location between the 400 and 500 hallway. AED team, please report at this time the location between the 400 and 500 hallway. Thank you.
Train of thought. I saw a really, really cool way that I had not seen in any of the other classes as well. This was really cool. And I just wanted to highlight this. There are so many good ways to think about how to do this, to kind of like conceptualize what is going on here. There isn't like one catch-all way to think about this. And so this other solution method, which I'm going to credit Haddon, this was really good thinking on his part of how to set this up. He actually didn't even use the fact that R was this 6.7%, that this 6.7% was related to the R. Instead, we said, okay, well, our A of t is equal to this 1356 e to the, now, I know that if I'm talking about half-life, that R is the ln of 1/2 divided by this t hat times t. So using that other definition of R. And then we used instead this 6.7% decay to figure out what's going on at a particular time. We filled in all of the unknowns. In particular, when t equals 1, so A of 1 was equal to whatever 6.7% less of this initial amount, so 1356 times 1 minus 0.067, which was equal to, what did this end up coming out to? 12.148. Okay, so we set up this equation instead. That 1265.148 was equal to 1356 times E to the ln of 1/2 over t hat times, in this case, we know our t value here, it's just 1. When t is equal to 1, our output is this particular output that we see. That's fantastic. And so all we're doing here is solving for that little t hat that's underneath. This would be like solving for r, but we don't even need to really solve for r. We're just solving for that little t hat there. And so dividing both sides by this 1356, get 1265.148 over 1356 is equal to e to the ln of 1/2 over t hat times 1, which I'm going to go ahead and actually just stop writing because times 1 just doesn't change anything. And then rewriting this statement as a logarithm, we get that the ln of this whole thing over 1356 is equal to the ln of 1/2 over t hat. And solving for t hat, that t hat was equal to the ln of 1/2 over the ln of 1265.148 over 1356, which also gives us 10.35 months. This is a really good technique. Actually, this is what we're really going to be doing for most of today, is this kind of methodology of solving, where we take a point and use it to gain some kind of information about R. Right? We'll have very almost complete formulas. We'll just be missing what's going on with R. And if I don't know what's going on with R, but I do know a value of X and Y, a value of our input and our output that I can plug in, then I can make R my only unknown, and I can focus on first solving for R before doing whatever I need to do with my formula afterwards. In this case, we actually were done after we solved for R, basically done after we solved for R. We wanted to find a component of R, which, this is exactly what this was. I thought that was a really creative way to kind of think about it. It was really nice. Yeah, Simran. From here to here? Yeah, that's just rewriting it as a logarithm, exactly. Exactly. If keeping track of all the fractions confuses you, which is fair, there's a lot of fractions to keep track of, you can start like entering that into your calculator, putting in the decimal. I really do encourage you, though, to be very, very careful about rounding. I would say if you are going to use the decimal form, so for instance, if we were to plug in whatever 1265.148 is, which is rounded, divided by 1356, I get 0.9, probably 0.93 repeating would be my guess if we hadn't rounded. Could be wrong about that, but would be my guess. And I would just say be very careful. You can put in ln of 0.933, but what I would actually do for your calculator is go up and copy your answer and then do like ln of that copied answer, just so you don't lose precision to rounding. When we round, it's probably a good idea to save rounding until the very, very end. And if you can avoid rounding entirely, then I would try to avoid rounding entirely. But I realize some of our calculators are maybe not set up to be able to handle inputting things like this into them. So we sometimes have to make concessions. That's okay. I recognize that. And to that end, I would say just do your best to save that rounding until the very, very end and keep as much precision as you can as you kind of work through. But this is really cool. This is a clever way of going about it. All right. Overall, I'd say good work. This was good. And I think it's really cool that we ended up with 3 kind of very different approaches that required us to kind of notice very different things about this. But this was good. Questions from the bell work? the main connection that I wanted you guys to see here was that that percentage change is still this R. Like this R that we're talking about is still some kind of percentage change over some unit of time, right? We lost that, I think, a little bit yesterday with looking at like the ln of 1/2 over t hat. That doesn't look like percentage change. And you're right, it's not percentage change when we are talking about it in that regard. But we could enter that into our calculator, and the R that we would get would be percentage change. It would tell us the percent at which we were changing over some kind of unit of time. So just to kind of reinforce that connection, this R can kind of mean a lot of things, but ultimately its original meaning was percent growth or percent decay. All right. I keep forgetting to erase this. That's okay. So we are going to be looking today at one more kind of example. So we did half-life doubling time as kind of our first application of our logarithms and our exponential functions. Our second application here is going to be something called Newton's law of cooling. The very basic premise of this is something that you guys have probably just found to be very, very intuitive. What happens when you take a really, really hot object, let's say like a cookie sheet that's been in the oven, and you set it out in a cool room? It cools down. Is there a limit to how cold it's going to get? Yeah, what is that limit? Yeah, the room's temperature, right? So we would expect for it to lose heat based on and kind of approach that what I'm going to describe as the ambient temperature of the room. So when I say the word ambient temperature, that's just like the surrounding immediate temperature, whatever the temperature is of the environment. Right. We get the exact same phenomenon when we take a really cold object and put it in a warm room as well, right? We see the temperature starts to approach what we see for, again, that kind of surrounding temperature. And it turns out that this process, this kind of temperature change, is exponential. That there is an exponential model that works to describe how that temperature is kind of changing for these particular objects. All right, so we're going to explain this as we go. One of the confusing things about this is that there are two T's that we're going to be working with. We're talking about a change in temperature as a function of time. So big T is going to be temperature, little t is referring to time. Big T is our output, little t is our input. So this is T of T, just to make things fun and not confusing at all, where big T here is our temperature, and little t here is our time. This is going to follow our standard exponential model. So this is still a times e to the RT. But there is a slight difference, except it's not really a difference, but it's like a very, very slight difference. Plus what we are going to label as T sub S, which is the surrounding, or as I will call it, the ambient temperature, which is just like the temperature of the room. Okay. This looks a little bit different than most of the exponential models that we have been working with. In particular, that plus T sub S feels a little bit out of place. Like we haven't really seen that in any of our other models, right? They've just been like these purely exponential models. And that is because the output temperature of our object is actually not the thing that is being subject to the exponential change. Right? The output itself is not what's changing. In particular, what's changing, if we were to say, take what we have there, so this is our T of T, think of this as like current temperature equal to a times e to the RT plus T sub S. If we were to subtract T sub S from both sides, you would get that our current temperature minus the surrounding temperature, or in other words, the difference in temperature, is equal to just purely this exponential piece, A times e to the RT. So what we're really looking at here is is not just what's going on with the temperature, it's what's happening to the difference in the temperature. So what's happening to how my warm lunch compares to the surrounding temperature of the room. Right. For that reason, A is not the initial temperature of the object, but is instead the initial difference in temperature. So in particular here, A is going to be equal to the initial temperature of our object minus the surrounding temperature. So it's that initial difference in temperature that we are looking at here. So still like the initial amount. It's just now the initial amount is a little bit complicated. It's the initial difference in temperature. And then also, just to make matters fun, we'll generally see it written as this, because oftentimes the thing that we want to solve for is the temperature of the object, not the difference in the temperature of the object and the surrounding temperature. So you'll more often than not see it written like this, but just kind of know that T sub S really kind of belongs on the other side, because what we are really kind of modeling here is a change in the difference of the temperature, not like the object's temperature itself. All right, questions about our pieces here, kind of how they're arranged, before we start taking a look at some examples. All right. So let's take a look here at example 2A. And I'm just going to go ahead and rewrite what we had there. This was T of little t equal to A times e to the RT plus that surrounding temperature T sub S, where, just a reminder, A is that initial difference in temperature. All right. In the case of 2A, we are told that a pitcher of water at 40 degrees Fahrenheit is placed into a 70-degree room. This actually already gives us a ton of information, right? In particular, if we're trying to build this equation, what information have we just been given here? So we just got T sub S. And I agree that we also did just get A, but why did we get A? What was the other component to A that we got? The initial temperature, that T of 0. So what is our surrounding temperature here? 70 degrees Fahrenheit. We're going to end up dropping, just for the math purposes of it, we'll leave off the degrees Fahrenheit through our formula, but yeah, it's important to note. And then our initial temperature here, 40 degrees Fahrenheit. Very cool. And so what is our formula going to look like? Well, T of little t equal to, what is this value of A going to be? Negative 30. It's actually very important that we get the order right here. We do want this to be negative 30 times e to the RT, don't know what R is yet, plus 70. It's important that that 30 is negative, because our object is warming up to be 70 degrees, which means that it should never be more than 70 degrees. If the 30 were positive, we'd be looking at an object that is cooling down to 70 degrees, where it would never be below 70 degrees. So whether it's positive or negative here, actually very, very significant. It's going to determine whether or not we can even take the, rewrite things as logarithms, basically. But in this case, yeah, negative because we are warming up to 70 degrees. All right. Another interesting thing that I'd like to, we actually kind of already mentioned this. If the object that I place in the room approaches the temperature of the room, right? We place a 5,000 degree knife in a room, it cools, it approaches that 70 degrees. What is happening to the difference as we kind of approach this? It's getting smaller. It is decaying. And so what should be true about this value of R for every single one of these Newton's law of cooling problems? They should always be negative, because the difference between the object's temperature and the surrounding temperature should always be approaching zero. It should always be getting smaller and smaller and smaller. These are always decay models, every single one. So this is just like a little gut check. If you get an R value that is positive, something went wrong. Now, our R values aren't necessarily going to have negatives attached to them. They're going to be logarithms, but there'll be logarithms that have a negative value. In particular, there'll be logarithms of things that are less than 1, which would give us negatives. All right. So looking at my formula here, this is really nice. What am I missing? I'm missing R. So T is just like X. So that's going to be a variable. We're not really going to be super worried about it. Big T is temperature. That's like Y. So that's going to be our output. Again, we're not really supposed to have access to that. The piece of our formula that we are still missing here is R. So we're going to need to devote kind of the first little bit of this solving process to identifying what is this value of R that we are still missing here. This is very similar to actually what Haddon's approach was for the bell work here. To solve for R, we're going to take a known value of the temperature at a known time and use that to figure out what R would need to be, and like plug those in for temperature and time, see what R would need to be. In particular here, what is the piece of information? What is the time that goes with a known temperature? So T of 1 should give us 45 degrees. Important to note, if 1 is our T value, what units are we using? We're going to use hours, all right, just to be consistent, right? We could also have 60 be our T value here and be using minutes, but we would just need to make sure that when we plug in for T, we plug in minutes. Just like a quick thing to know. All right, very good. And so how are we going to use this to actually find R? Well, this tells us that 45 should be equal to negative 30 e to the R times 1 plus 7. You feel okay about what I just did? Understand why? Really, the purpose here is we go from 3 unknowns to 1 unknown. Now we can solve for R. Right, so filling in a known piece. This is like what we did when we were doing like the y equals mx plus b. To solve for b, you take a known value of x and a known value of y, plug them in, solve for b. Exact same thing here. We're plugging those in. Now we're solving for R. How do I solve this for R? What do I need to do to solve this? Second, subtract 70 and divide by negative 30. We need to get the exponential piece of our equation on its own. Subtracting by 70, 45 minus 70, I get negative 25. And dividing by negative 30, I get 25 over 30, or 5 over 6. And then e to the r times 1 is just e to the r. If this happened after 2 hours, it would be 2R. If it happened after 7 hours, 7R, so on. So we did, first we subtracted 70. So 45 minus 70 was negative 25. And then negative 25 divided by negative 30. You could leave that as 25 over 30. I simplified it down to 5 over 6 just because I'm going to have to be writing it a lot. So 45 minus 70 was negative 25. And then dividing by negative 30, I got either, you could leave it as 25 over 30, but I canceled out a 5 and wrote it as 5 over 6. And the reason we're doing that is to get this exponential bit, that e to the power of whatever on its own. In this case, e to just the power of r, which is nice. So what do I have to do? I've got number is equal to e to a power. How do I access that power? How do I isolate what's going on in the exponent? Rewrite it as a logarithm. Love it. What is this going to look like? Equals r. Oftentimes, again, this one was nice because the value of t was 1. Oftentimes you'd have like something to multiply or divide here, but I gave you a nice value of t, so that's it. That's our value of r. Let's gut check ourselves. ln of 5 over 6, is this going to be positive or negative? Negative. How do we know it's going to be negative? Less than 1. ln of anything less than 1 is going to be a negative number. You could confirm that when I do the ln of 5 over 6, I get that this is negative 0.18232, blah, 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 blah. All right, very good. And so our formula, we're going to update it. We found that value of r. I get that t of t should now be equal to still negative 30 e, but now to the ln of 5 over 6 times t plus 70. So first step, we put as much information as we could and then use that kind of known value of x, known value of y to find r. Second step is going to be to figure out how long it takes for the temperature to actually rise to 60 degrees. So we're actually solving the problem here, right? Now, what are we being given here? We're being given big T, and we are looking for little t, looking for small t. So plugging in 60 into big T. So this is going to be, instead of T of T, I'm going to write 60 is equal to negative 30 e to the ln of 5 over 6 times t plus 70. We're still trying to solve for something in the exponent here. Before, we were solving for r. Now we're solving for t. So before we knew t and tried to solve for r, now we know r and are trying to solve for t. All right. So what do I need to do? Exact same thing as before. Subtract 70 and divide by negative 30. 60 minus 70 is, divided by negative 30 is 1 over 3. $60 minus 70, negative 10. Negative 10 divided by negative 30, 1/3. Negative 10 divided by negative 30, so 2 negatives. Yeah, which is very important. We want to make sure, because if we ever did get a negative as our result here, we'd be in trouble because we can't take the ln of a negative. So it's very important that we got this in the way that we did. To be as precise as possible, to make sure you're not rounding prematurely, I would write this as ln of 5/6, personally. All right. And then what do I do here? How do I access the exponent? How do I solve for t? Before we do that, we have to rewrite this as a logarithm. Yeah, so rewriting this as a logarithm, I get that the ln of 1/3 is equal to the ln of 5/6 times t, and that t is equal to the ln of 1/3 divided by the ln of 5/6 hours. Do I get to cancel the ln's? ln divided by ln, I get to cancel them, right? No. Can't do that. Do I get to combine these with my quotient rule? No, I do not. The only division that the quotient rule talks about is where? Inside the logarithm. So for instance, I could split apart what I have here. I could write ln of 1/3 as ln of 1 minus ln of 3. Certainly could do that. We could write the denominator here as ln of 5 minus ln of 6. That would work. But I can't split apart anything else. I can't do anything else there. And this is really just like, as cool as that is, as precise as that is, it's not a very useful time metric. And so you'd realistically plug that into your calculator. And when I do that, I get that this is like 6.03 hours or something, or 6.02 hours. Ln of 1/3 divided by ln of 5/6. Yes. This one. Which you just plug into your calculator. It's about 6 hours. Yes, Dylan. Yeah, that's probably good. I mean, if you said this hours, then like I'd probably give you full credit for it, but it's not like a very digestible answer, right? It's probably better to at that stage bite the bullet, round a little bit. We're just going to call this 6.03 hours. If I wanted to be really mean, I could give you like an initial time. Like I tell you, oh, we put this object in here at 2 o'clock. Tell me when, tell me the time that would be measuring when you would hit that last one. That could be a fun question that I could ask you. And then you'd need to convert not just a number of hours, you'd also need to then convert that into a time. So what would 6.03 hours later be in terms of number of hours, number of minutes? That could be fun. Or maybe like, the tail end of like a test problem, who knows? Just like worth like a point or two, at the end of a test problem. All right. Good question, though. Other questions here? I actually do have a quick thing that I want to mention. I meant to mention it during the bell work, and I forgot. One technique that I didn't see, which is fair, but one that I do want to highlight because this is a mistake that I saw on that I have seen people make in the past, not just in this class, but just in general. It's not a bad idea, but there's a very, very key reason why it doesn't work. So thinking back to this decay problem, if I'm looking at the half-life, how much of my stuff has decayed away? Half of it, or as a percentage, 50%. So can I take my 50% and say, well, I could just figure out the number of 6.7% decays that I need in order to get 50%. 50 divided by 6.7%, this is about 7.3 times that I'm going to need to decay by this amount in order to get to 50%. Does this work? Okay. So Dylan has correctly identified the issue here, which is that this would be assuming that our model was linear. In other words, what assumption have I made about the size of each of these 6.7%? That they're all equal, that our rate of change is constant, that our function is symmetric. In reality, what is happening to the size of each of my subsequent 6.7% as I am decaying them? They're getting smaller. 6.7% of a smaller thing is going to be a little bit smaller. And so as we decay, this 6.7% ends up being less and less and less and less, which is why the actual answer was longer than the answer that we saw here, because it doesn't quite actually get us that far. So I think an understandable pitfall. Certainly not a bad idea to try. I think it's a really good idea, but recognizing here that this would only work if this 6.7% that we're talking about was staying the same size, when in fact it is getting smaller and smaller and smaller and smaller each time we take it. So just a cool little thing that came up earlier that I wanted to highlight. All right, but back to the bulk of what we were doing. Any questions with regards to our Newton's law of cooling setup? So very, very similar to our half-life setup. We start by finding R. In this case, R is maybe a little bit messier than with our half-life, but really the exact same idea. For finding R, we're going to use a known value of little t and a known value of big T in order to make R the only thing that we need to solve for, and then we solve it. Right? So we start by filling in what is R, and then we're going to use that kind of completed formula there to figure out what is going on next. All right, let's take a stab at B then. I'm going to get you guys started on B, and then I'm going to give you some time to kind of work on it yourself. The setup, I would say, for B is a little bit trickier, kind of that initial setup, but then once we hit the ground running, it should be fine. I also do want to note, when I was writing this problem, I think I made the assumption, either I forgot the information, which is entirely possible. I may have just forgotten to include it. But I think I was making the assumption that this value for R that we found is dependent on the type of object that we are working with. So for instance, water would have one value of R, or wood would have one value of R, or this calculator would have one particular value of R, and that value of R would carry through all the way through. When in actuality, if I take a really, really cold object and put it in a warm room versus taking a really cold object and putting it in a very, very hot room, what's true about the rates there? Which would we expect to get warmer faster? In the hotter room, we would expect it to be, getting hotter faster, because that difference in temperature starts out larger. And so it's not necessarily just object related. And so the piece of information that I give us to be able to solve B is that is that extra little piece that we'll need to find that R value, which is that after 30 minutes, we're going to be at a temperature of 52 degrees. Okay, but you'll get to that during the solving process. Just wanted to make sure that's not on your paper. You do need it. Is this data point right there. Okay, so let's parse through what we're looking at with B. So 2 hours after the pitcher from part A that we're talking about was placed in the room, the heat kicked on and the room warmed up to 75 degrees Fahrenheit. Now we're going to assume that as soon as the heat kicked on, the room instantaneously changed from 70 degrees to 75. We're just going to say it just spiked all the way up instantly to 75. Obviously, that wouldn't actually be how that would work, but then we're modeling like this weird growth that is changing based on like other growth that is going on, and that's a mess, and that's like a partial differential equations problem, and we're not going to do that. So we're just going to assume temperature is now suddenly automatically 75 degrees. And then we're trying to figure out what's going on after another 2 hours in the room. So changing the ambient temperature like this is actually pretty problematic. There's not like an easy way to take our original formula and work in the fact that the ambient temperature has changed. Really, as soon as the ambient temperature changes, we're basically starting from scratch. We're starting over with a new initial temperature, with a new ambient temperature, a new surrounding temperature, and we're just going to work from there. So what is my new initial temperature? How would I find the temperature of my pitcher of water as soon as that heat kicked on? What do I need to do? So is the pitcher of water still at 40 degrees after having sat in that room? Okay, so we're actually going to need to use part A, the equation that we got for part A, to figure out our starting temperature of the water here. And then we can use that to subtract from 75 and find our new value of A here. All right. So in particular, our new T sub 0, I'm gonna call this T sub n of 0, just to note that this is like our new starting temperature. All right, if you don't want to use the sub n, that's fine. Just note that this T of 0 and the T of 0 that we have up here are not the same. Right. But what is this new starting point the same as? Well, it was using our old equation, that old T, for how long? 2 hours. So that was T of 2. Okay, well, that's not too bad. T of 2 is just going to be negative 30 e to the ln of 5/6 times 2 plus 70. Yes. So that's just my way of saying we have a new starting temperature. So the n stands for that this is a new starting temperature. You can, if it confuses you, if the n confuses you, you can leave it off. I just am trying to highlight that the T0 that we see up here is not the same as the one that we're getting down here, even though we're using a piece of that old equation. All right. And this is done. This is just a number, right? There are no variables here. This is just a thing that you could plug into your calculator. And when I do, I get, I'm doing this like I haven't done it before today. That's, I'm just confirming, times 2 plus 70. I get that this is equal to 49.16 repeating degrees Fahrenheit. That's just taking that value, plugging it into your calculator, see what you get. I would highly recommend plugging this one into your calculator because, man, if you try and keep that precise throughout, this problem is going to turn into a mess real fast. So I actually would leave it like this. If you wanted to round this to like 49.17, you probably could. I'm not going to round it. I'm going to leave this as 49.16 repeating. All right. What is our new, I'm going to label this as T sub NS for the new surrounding temperature, just again to be kind of consistent with this notation. What's our new surrounding temperature here? That's 75 degrees Fahrenheit. And so what is our value of A going to be? Yeah, this is going to be that 49.16 repeating minus 75. I get negative 25.8. And if I'm doing 0.6 repeating, I'm going to say 0.83 repeating. And so what is our shell of a function going to look like? What is our new function for temperature? I'm using NS to be new surrounding temperature. Very good. And so we have a new value of R defined. Again, the piece of information for that right here, that after 30 minutes, T is equal to 52 degrees Fahrenheit. 30 minutes, what would a good value of T be for 30 minutes? I like 0.5, I like 1/2. Alternatively, if we chose to use 30, what would we need to be very careful of when we're plugging in 2 hours? We'd want to use 120 minutes if we were going to use 30 minutes, or we use 0.5 hours if we want to plug in 2 hours. So just making sure that our time is kind of consistent there, that we're keeping our unit straight. So that is the problem. I'm going to give you guys about 10 minutes, find R, and then figure out what the temperature is going to be after an additional 2 hours in this now warmer room. Yes. Yeah. Okay, for these. Yeah.
And I just want to make sure, like, if I
So like taking the ln of both sides and then like dropping the x down. That's totally fine.
Okay.
Now you want to be very, very careful when you divide here. What we are dividing is not the contents, it's the logarithms themselves. So what you'll get is when you have x ln of 2 equal to the ln of 53. Dividing by the ln of 2, you get x equals ln of 53 over the ln of 2, and we can't do anything to simplify this. Okay. This is your final. So just be very, very careful that you don't like divide by the contents of the logarithms. Okay. Yeah. But otherwise, yeah, you can totally do it. So when T is 1/2, what is the temperature going to be? It's kind of hard to see. I'll see. So that's your output. So that goes, that's going to be, that's going to be, that's, yeah. Yes. 32. No, 52 is equal to this. So T of 1/2, yeah, so T of 1/2 is this. Okay. But it's also 52, and so you set those two equal to each other. Yeah. Note here, just in terms of like the notation, when I'm saying that T is equal to 52 at 30 minutes, that is equivalent to me saying that T of 1/2 is equal to 52. All right, so So you don't get like 52 of 1/2 or things like that. You don't actually like directly substitute in for the t piece. I'm saying the output is 52. That whole y output is 52. So t of 1/2. So 40 was that initial temperature, which was put into this table. So if we say this negative 30, that's where the point is, because it's 40 minus there's a 7. Which was 40 minus, it's that initial difference. So it's never on its own. Yeah, you did. Oh, you're actually doing algebra subtraction. Yeah. Yeah. So it's that initial it's the initial difference, which is t of 0 minus t. Yes. Oh, goodness. This looks great. Very valuable. Yeah, that's perfect. I said oh, goodness. Okay, so what are we missing? Okay, and so this is like our output. This t is our input, so our x value. So really the only piece of the formula that we're missing that's not a variable is this r. So how did I find my r value? So I was missing my r value up here. So what did I do to find that r value? 5 degrees after now. So we plugged in 45 and then 1. Cool. So what do I have to plug in here that would be like a time that I know and a temperature that goes along? Exactly. Sorry. Yeah, that's it. And then solving for that. What was this one? This was figuring out what that new initial temperature was going to be. So that was to get us started. That was saying, hey, yeah, that's giving us that t of 0, that new t of 0, which isn't technically like, if we were to model this whole thing, like if I were to give you a really, really nasty moment, right? And it was, you have an object sitting in a room, and I want to know what happens, what the temperature of that object is 4 hours later, when 2 hours into this modeling project, the temperature increases by a certain amount. Then how would you do that? Well, you first would need to figure out what happened in the first 2 hours, and that's your new start point, and then you're looking at what happened in the next 2 hours. Yeah. Yes. Yeah. Yeah, exactly. Basically, yeah. I mean, not basically, yes. Exactly. Yes. So this looks super good. And then the question is, do we know what this temperature is when our value is 1/2? What is that corresponding temperature going to be? Which part? Yeah, it's 52. So we set this equal to 52, and then we're solving for it. Great. This looks good. Rewriting this as a logarithm. Looks good.
I guess more budget or what I'm realizing that I probably should just leave it as this.
I'd probably leave it at that. And then so subtract.
Right.
3 over. Yeah.
Yeah, I did all that.
Yeah, perfect. And then what are we doing with this value bar?
Plugging it in.
Plugging it back in, and then we're plugging in
2 hours instead of
2 hours and 13 minutes.
So I don't leave 52 like that because I'm solving for
You'll
this.
find a new temperature.
I'm solving for this.
Yeah, you're looking for what that new temperature will be. If I gave you a temperature, then you would plug in that new temperature there, but you're looking for the temperature, so we'll just evaluate and see what that becomes. How you doing?
I'm just trying to figure out.
Okay.
I can see the rest of the board.
Sure. You want me to zoom out? Yes. So T of 2 is what we're looking for. So in order to find that, we're going to need this missing R value here. So first we'll need to find the R value, and then we'll plug in 2 and see what all that works out to. And to find the R value, so for instance up here, how did I find my R value? What did I do to go from here to here? Okay, so we had a known value of Y and a known value of X, or, big T, little t. And we plugged those in, and then R was the only thing we didn't know. Do we have a known value of big T and a known value of little t that we never got together? Yeah, exactly. So when our temperature is 52, when T is equal to, our temperature is 52, when our time is 30. If we want to use 30, we can. We just have to be careful to let the units here and the units here to match. So you could do 30 here and then 120 here. That would. Or you could do 2 there and then 1/2 for your time. So T of 2 will be what we do at the very end. So first we need to find R, which is what happens when our time is, if you're going to use 2 here, I would use half of an hour here. So what are we setting for? 52 would be equal to blah, 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 blah. Except I'm not able to. Okay, cool. So this piece of, okay, that's fine. uh, I'm gonna, we'll go through this really quickly. How did we solve for R? What did we have to do? We had to set it equal to 52 and plugged in what for our value of T? Plugged in either 30 or 1/2, depending on what we want. So 52 was equal to negative 25.83 repeating e to the 1/2 of R plus 75. From this, I get that 23 over 25.83 repeating is equal to e to the 1/2 r. Double check that, subtract 75, divide by this coefficient, and that r is equal to, skipping steps here, 2 ln of 23 over 25.83 repeating, which is rewriting as a logarithm and then multiplying by 2.
I think it's 52.
52 was the y value that we were given. It was t is equal to 1/2 and big T is equal to 52. It's not on your paper. I had to add it. Yeah. That's like the extra piece of information.
Oh, that was the.
Yeah, that was the highlighted scribble bit. And so from this, what do I end up plugging into t to find my final answer? So this is t of 2 is equal to, I get negative 25.83 repeating e to the, in this case, 4, which is 2 times 2 ln of 23 over 25.83 repeating, plus 75. What is our final temperature here? 7776, something like that, degrees. One of those two. Any rounding, you might have been off by a couple of tenths or a couple of hundredths or something. But what we get there. So this was 2. All right, have a fantastic rest of your day, guys. And unfortunately, I will not be able to get that because my computer decided it wanted to die. So sorry about that to my recording friends, but we will end that